אבל אתם מבינים כמה שהאתר לא מותקן.
מה?
האתר המצגת? לעשות share screen מהמצגת?
כן, כן,
שאלה אם שתפעיל את זה עכשיו, לשתף את מה שתפעיל או שלפעיל את זה.
זהו, זה עכשיו.
זה קצת לא אידיאלי, אבל אני מעדיפה לשבת.
יאללה. כן, איך מעלימים?
את הזה,
תיכנס למעלה לשלוש נקודות ותעשה הייד, לא, על 3 נקודות ושלוש נקודות למעלה. תעלה למעלה את הפוינטר, תעלה עוד טיפה למעלה.
למה זה לא זז, אבריאל?
יש דיליי, יש דיליי. כשאתה בזום יש דיליי.
יש דיליי.
זה לא זז.
הנה, את 3 נקודות והייד וידאו פאנל. למטה, תראה עוד. הייד וידאו פאנל, אחד מתחתך. יוצא את הפאנל. כמובן שאני יודעת כי עשו את זה בכיתה שלי. זה היה רחוק מדי. תקליט, נראה לי שכולם פה...
כן, גם בזום יש.
תגיד אז מה אני מעדיפה באנגלית?
מעדיפה באנגלית?
טוב, שלום לכולם. אנחנו שמחים מאוד לארח את נופר קרמלי. נופר סיימה את הדוקטורט שלה בטכניון ב-2020 תחת הנחייתו של בני קימלפלד. היא פוסט-דוקטורנטית ב-ENS בפריז, זכתה בגוגל PhD פלושיפ ובג'ייקובס פלושיפ בין היתר, ואנחנו מאוד שמחים לארח אותה פה היום. היא תדבר על fine grained complexity of answering database queries. ובמה שלך נפרד.
תודה. טוב, אני אתחיל בעמידה, אבל אני כנראה אשב באיזשהו שלב, כי יהיה לי יותר נוח.
להוריד את המסכה.
להוריד את המסכה?
כן, אז כדי שנבין משהו.
ואני אעבור לאנגלית, נראה לי, כי פשוט יהיה לי הרבה יותר קל עם עולם המושגים וכאלה. So this context of this talk is a theory of databases, and we know we have a lot of data in the world. We get more and more every year. So if we have a lot of data, sometimes it's not enough for us to say that we have a polynomial time algorithm that solves something. And this is why we talk about the fine-grained complexity of answering queries over data. The plan of this presentation is as follows. I'm going to start with some introduction about the very basic building blocks of queries. And we will see what we know about the complexity of answering these building blocks. And we'll see a key notion for this, which is called the acyclicity. We'll understand the basic challenges. And then we'll slowly increase the expressivity of the queries we handle, and we'll see different solutions and how the complexity changes. This will be the first part of the talk where we want to enumerate all answers to a query. And then in the second part, we'll also mention some other tasks where we want to do something beyond just printing all of the answers. And feel free to stop me for questions. Okay. Let's start with the introduction. So here's an example for a database. It has tables containing information. These tables are modeled as relations. And a very basic building blocks of queries is join. We want to join these two tables. It can be written as so. This is a join query. And then what we want to compute is we want to join the two tables on the joint attributes, the attributes that they have in common. And then we will get all combinations of a tuple from here and a tuple from there if they agree on the joint attributes. This is what we want to compute. What are the challenges when we want to compute such things? So these are a few things to keep in mind later when we inspect the complexity. So first of all, we should be aware that if we want to join these two tables, R and S, and it so happens that all tuples agree on the join attributes, it means that the size of our output would be the size of R times the size of S. So the output can be quadratic in the size of the input we start with, meaning we can't hope to have an algorithm that runs in linear time and always prints all of the answers. Just printing them will take longer. And another thing we should take into account is that even if we don't have a lot of answers at the end, if we're not careful, we can have a lot of intermediate answers. For example, if we want the join of these three relations, and the way we do that is we first join the two, we get this, and then we join the result with this, with the third one, then even though we only have one answer at the end, we went through a lot of intermediate answers and wasted a lot of time on their computation. So something we can notice here, that will be a spoiler for later, is that we have these dangling tuples. These are tuples that are part of our input, but they don't participate in the output of the specific query we want to compute. And if we had a way of efficiently identifying them and removing them before we start the computation, this means we wouldn't produce all of these intermediate answers and the computation would be much more efficient. Okay, so we have these things to keep in mind. What does it mean about the complexity? How do we formulate the complexity? So first of all, we do need to read the input before we know for sure whether we have a first answer or not. And we do need to print every answer. So a very natural complexity measure that we will look at is trying to answer the queries with linear time before the first answer and then constant time between answers. We call this linear preprocessing and constant delay. And we want to ask, when can we solve queries within these timelines? And here the notion of a cyclicity is very important because acyclic queries can be solved within these timelines. So what is an acyclic query? A query is called acyclic if it has a joint tree. A joint tree is a graph that describes a query where there is a node for every relation. This graph is a tree. And if we look at every attribute and we look only at the nodes that contain these attributes, these nodes are connected. We have a subtree for every attribute. So this query is acyclic because it has a joint tree, but not all queries are acyclic. We consider this query in the bottom here. If we want a joint tree, we need these 3 nodes. If we want it to be a tree, we need 2 out of the 3 possible edges. And no matter which edge I choose to leave out, I will have some attribute that is not connected. So this query is cyclic. Why are cyclic joins easy? Well, we have an algorithm that solves them very efficiently. It's a quite well-known algorithm. So let's say this is our input. We want to join these 3 tables. Start with a join tree. We set some root arbitrarily. And then we have some process that removes the dangling tuples very efficiently in linear time. It's called a semi-join reduction, where it has several names. But basically what it does is it goes, first of all, it scans the trees from the leaf to the root, and it filters every parent according to its child. So for example, here, we can see that there is no B3 value in the table on the top. So we know that in its parents, the tuple that contains B3 will never be used. So we can just remove that. And then we filter the parents according to the other child. And once we're done with the root, we go down from the root to the children and filter the children according to the parents. This process is guaranteed to remove all of the dangling tuples. And then we just need to join along this tree, which is something we can do very efficiently with constant delay. But this process that I just described only works with joint trees. We try to do the same thing over the same input, but we use a different tree that is not a joint tree. For example, here you can see that the C attribute is not connected. Then the same process will remove only some of the dangling tuples and not all of them. Because intuitively what it means is that the information about the available C values doesn't propagate along the tree. So we have an efficient algorithm for acyclic joins. This algorithm doesn't work anymore for cyclic joins. Does it mean that cyclic joins are harder than acyclic joins, or is it just that we don't have the right algorithm and we need to keep looking? So let's say we think, we can't find a good algorithm. Well, at some point we would like to be able to prove that it's hard, that we don't find an algorithm because such an algorithm doesn't exist. How do we do that? So for hardness proof, we start with some assumptions, and then we prove that something else is hard based on these assumptions. So if we wanted to show that something cannot be done in polynomial time, we would assume P is different than NP, and then show some reduction and conclude that our thing cannot be done in polynomial time. But now we're interested in fine-grained complexity. So we need a different type of assumption. And this is why we're sort of users of the type of research that's done in the field of fine-grained complexity, where they look at very basic problems that were well studied for a long time and try to reason about how hard they are, which problems are equivalent to which other problems, and what are reasonable assumptions to use. So we start with some assumptions on basic problems on graphs, and then we try to use these assumptions to show that our queries are hard. So for example, if we look at this cyclic query that we saw before, how do we prove that it's hard? We start with the assumption that we cannot detect triangles in a graph in linear time. And then let's say we have a graph, we want to know whether it contains a triangle. We can just encode all of the edges in all of our three relations. And then what this query computes by definition is all of the triangles. So if I can find a first answer to this query in linear time, it means I can find a triangle in linear time, which is something that I assume I cannot do, meaning this cyclic query is hard. But this is just an example of how I prove that this specific cyclic query is hard. What happens with other cyclic queries? Well, we have a proof that every cyclic query is hard if we assume a generalization of this assumption. So we assume that it's hard to detect hyperclicks in a hypergraph, and then we have a reduction that always works.
So Nofar, you're talking about hardness in data complexity?
Yes.
So what's the order of quantification here? Like so you fix a query,
Yes.
any query that I fix and it's cyclic, there exists a data set for which it's hard.
Yes. So I look at a specific query. I think I will clarify it in a few slides, but I'll already. Okay, I'll clarify it in a few slides, and then we'll see again if it's not clear.
But still, can you use the same the triangle for everyone? K minus 2 dummy verbs.
If you have a longer cycle, you can use the triangle. But if you have a hyperclick, like you have four nodes, such that every three of them are contained in a hyperedge, then you can no longer encode the triangle.
No, I meant to prove an hardness. It would take a specific instance where I add k minus 2 dummy variables that all k edges contain them, and then it's equivalent to triangle. Isn't it? It's not true.
But then you see, you not get into the k minus 1.
Oh, this is into the k hardness. It's not the square hardness. How hard is it? Cannot find all of them.
And the number of edges.
Oh, okay, I see.
Okay. So far what we have when we look at these type of joint queries, if the query is we have a dichotomy. We consider every query as a problem, and we know whether this specific problem is easy or hard. It's easy if it's a cyclic, it can be solved in linear reprocessing time and constant delay. And if it's cyclic, it's hard. And when I say hard, I don't mean really hard. I just mean it cannot be solved with linear reprocessing and constant delay with this ideal guarantees, under the assumption that detecting hyperclicks. So far, the intuition I tried to give is that some queries have easier structures than other queries. And we know very well what happens in very basic cases, like what we saw now. We have a complete dichotomy, but we also want to reason about other more complicated cases. So the long-term.
Something missing. What is constant delay? Suppose the output is triangles or something like this. And so there are n-cube triangles.
Right.
So you cannot do it in constant delay.
So the total time will be n cubed. The total time will be the number of answers, but you will have a constant stream of answers that your algorithm produces. After only linear time and the size of your input, you will produce the first answer. And then immediately after that, you'll have another one and another one.
It's delays between us.
Yes. So the long-term question is what we would like to do. Imagine we're a system that wants to compute queries. We get a query from the user. We look at the structure of the query and we say, with this structure, we can achieve these time guarantees, and here is an algorithm that achieves that. And we know we cannot do worse than that because we have a hardness proof. We cannot do better than that because we have a hardness proof. But of course, we won't do all of this now. We will start with the more narrow parts. And here are some clarifications for the questions that were before. So in this talk, we only consider time complexity. We assume we're allowed to use as much space as we want within this time. We treat every query as a problem, where the input to this problem is the database. And in particular, for the measure, we use what is called data complexity, which means that we measure the time that it takes with respect to the size of the database. And we treat the size of the query as fixed, which is something quite common to do in databases because queries are usually quite small and databases can be much, much larger. We use the RAM model for computation, meaning we assume we can build a lookup table in linear time and then search it in constant time. And we will have this notation, lin const, where the first part is the amount of pre-processing we allow, linear in this case, and the second part is the time per answer or the delay, which is constant. So for this, this will denote the class of all problems that can be solved within these time bounds. So this was the introduction. And now we will increase the expressivity a bit and see what happens. We did it. Are there still more questions about the settings, how we look at things?
Yeah.
Clear?
I have a question.
Yeah.
You talked about the triangle detection as a sort of an example hard problem.
Yes.
But there the hardness was about finding the sort of the linear preprocessing. It was about the preprocessing.
Yes.
What about proving something about the hardness of the delay?
That's a good question. We will see a different kind of hardness-based results later in the talk, and then maybe in the conclusions we can also talk a bit more about.
Because I think that Yossi gave a reduction that was, I think, was correct if you only care about the preprocessing time, and maybe it doesn't satisfy all other requirements. But I think regarding linear processing time, I think your reduction was fine.
I have to say I didn't completely follow what you said.
No, but then
before,
it's
so-
not proportional to the number of edges. That's it.
Okay, I'll continue then. Okay, we increased the expressivity. So far, we only had joins. Now we're looking at what we call conjunctive queries. That's very classic, basic type of queries. And the thing we introduced here is projections. So basically, we have a join like before, and now one of our variables is existential. In this case, movie is existential, and the free variables are actor and year. So what this means here is that we have a database in this example that describes movies, which actors participated in which movies, and which movies were released in which years. We want to join these two tables and project out the name of the movie, meaning we get a list of actors and the years in which they were active. And something that's very important to mention here is that we use set semantics, which means that if the same actor participated in two different movies in the same year, we only want to print this answer once. We don't want to waste time on printing the same answer several times if we have several justifications for this answer. So what do we know about the complexity of conjunctive queries? First of all, the cases that were hard before are still hard. The query is cyclic, it's still hard under similar assumptions to what we had before. But now the cases that were easy before are not necessarily easy, it depends on the projections. We have a property that's called free connex, and this property exactly captures the tractable cases. There are some fine prints here. We only consider conjunctive queries that have no self-joins, meaning you can't use the same relation twice. I just say that so I won't lie to you, but I want to look at the big picture, so I won't go into these details, but we can talk about it later in the conclusions if it's of interest to everyone. Okay, so what are free conics queries? Free conics queries are queries that are cyclic. That's the definition we saw before. But they also have another requirement. We want the free variables to appear in a connected part of this tree. So either we have a subtree that contains exactly the free variables like we do here, or this query is also considered free conics. And the way we formalize this is we say we are allowed to add nodes that are subsets of existing nodes. And then we have a subtree that contains exactly the free variables. Why are free conics queries easy? Because we can do something very similar to what we did before. We have a join tree, we filter and remove the dangling tuples according to the join tree. And now, after I used all of the relations for the filtering, I can just ignore everything that's outside of this connected part with the free variables because I don't need it. These variables are not part of the input. And I can use what's left to join along that and solve what I want to. Why are queries that are not free conics hard? So here's an example for a basic query that's not free conics. And so just to start with some intuition, if this is our input, then the output only has one answer, even though I have two different ways of explaining this answer, where the y value is one, the y value is one, or the y value is two. And as I said, we don't want to spend time going over all of the explanations of this answer, but only constant time per answer. This is intuitively the hard part. Okay, but intuition is not enough. We want to prove. And as you said before, previously the proof was just looking at the pre-processing. But now we can't do this anymore because for cyclic queries, we can find the first answer in linear time. So what we do here is we look at the total time. So we start with the assumption that we cannot multiply two Boolean matrices too efficiently in quadratic time. And then we can encode the matrices in our database. So in the first relation, we will have the first matrix, and we will encode the indices of the ones. So for each one, we will have the row and the column where it appears. And the second relation will have the same matrix. And by definition, this query computes the results of matrix multiplication, the indices of where we have ones. To see this, you can see, for example, that the one in index 1, 2 can be explained by the ones in indices 1, 2, and 2. So if we can solve this query with linear preprocessing time and constant delay, since the size of the input is bound by n squared and the size of the output is bound by n squared, means overall we solve a Boolean matrix multiplication in quadratic time, which is something we assume cannot be done.
Okay. So just to ensure I understand, so the number of rows in the matrix is the number of entries in the database?
Yes.
So if the number
the number of entries in the database is the number of ones in the matrix.
No, but I mean, what are the dimensions of the matrix?
N by n.
And n is?
N is the dimensions of the matrix.
No,
And
how does it relate to the database?
So the database is size n squared
the
potentially?
database, worst case, it's size n
So
squared.
it has n rows and n columns and fields.
The database has n squared rows.
N squared.
Yes, and 2 columns,
I see.
row
So,
and column.
and we get an n squared by n squared matrix in this case.
No, you get, you mean in the database?
I mean, how do
You
you
start-
transform a table to a matrix?
You start with something that's n by n, and then you look at each one you have here. Here you have a 1 in index 1, 1, so you put 1, 1 as a tuple. You have a 1 in index 1, 2, you put 1, 2 as a tuple. You will have at most n squared ones, so the database will be at most of size n squared. Okay. So overall, what we get is assuming Boolean matrix multiplication is hard. We cannot find all of the answers in the time we wanted. So this proves that this specific query is hard.
So when you say Boolean, I mean end of all of ends, right? Not, it's not the, so it's not the usual method.
Just filter according to the zero.
No, but
No,
It's Boolean matrix multiplication.
it's Boolean, yes.
But
It's
it
all.
doesn't-
It's not
Yes.
ZF2.
But it doesn't have to be Boolean.
Yeah, it has to be Boolean because the one means that there is a one in the same row and column.
Something can be over the integers, not.
it's not Boolean, not like positive.
You
don't want minus.
Because multiplicity is return one.
Right, then just.
No, it's a weak sometimes.
Just cost another one.
Okay, so something I want us to notice here, so we will use it later, is we have here this sort of path X, Y, Z. I call it a path because X, Y are neighbors because they appear in the same atom, and Y, Z are neighbors because they appear in the same atom. So it's this path where the two variables on the edge are free variables and the variable in the middle is existential. And whenever a query is a cyclic but not free conic, we will have such a path. And whenever we have such a path, we can encode matrix multiplication. So this proof works for every query that's a cyclic and not free conic. And later, when I want to tell you that some query is hard, I will tell you, hey, look at this path. This shows that it's hard. So this is the dichotomy we saw before, and hopefully we have a bit more intuition now. Good. So let's go back to the example we had before. This is the example with the movies, and you can see that this query is a cyclic because it has a joint tree, but it is not free conics because we have this path actor, movie, year, where movie is projected. So this means I just told you that according to the dichotomy, it's hard, and we have a proof that it's hard. But now I'm going to show you an algorithm to solve it. And here is the algorithm. Let's say this is our input. We have linear preprocessing time. So we can go over the table release and build a lookup table. For each movie, we will get its release year. And then we'll go over the relation cast, and we will extend it with another column. For each movie, we will look up the year and add this here as another column. And now we can ask for this extended query. And this extended query is a cyclic and free conics. So from now on, we can do it with linear processing time again and constant delay. So it is easy. So what I just did is I proved that it's hard, and then I proved that it's easy. And my question is, how is that possible?
In the release table, so you only have 1 year per movie?
Good point. That's exactly the thing. I made an implicit assumption that in the release date, that every movie was only released in 1 year, wasn't released in more than 1 year. And this is actually something that's very common in data, and it's modeled in databases as functional dependencies. So it means that an attribute cannot have more than one attribute that's assigned to it. And functional dependencies do affect the complexity, like we see in this example here. So the reason this algorithm works, right, is because I had this dependency. Otherwise, without a dependency, it's possible that, let's say, the first movie has 10 different release years, and then if I don't want to lose answers, I have to duplicate this first tuple 10 times with all the different years, which is something that I cannot do in linear time. So this is why the algorithm only works with the dependencies, but let's also briefly mention why the hardest result doesn't work with the dependencies. So if here over the same construction, we have that X implies Y in R1, then it means that when I want to do this construction, I'm not allowed to assign 2 columns to the same row. So I'm not allowed to multiply matrices that have several ones in the same row, which is not general matrix multiplication. So we cannot encode matrix multiplication when we have functional dependencies as part of the schema of the database. So the hardest results do not hold when we have dependencies. So our question was, what happens to the complexity when we have functional dependencies? We wanted to understand this. And here are our results. If we look at unary functional dependencies, which is what we saw before, one attribute implies another. This was the dichotomy we had before, and this is the new dichotomy. We define some extension of the query, similar to what we saw in the example, and we managed to prove that the complexity of the original query depends exactly on the complexity of the extension, on the structure of the extension, the same way that the original dichotomy worked under the same assumptions. So the positive case, it's an algorithm that works a bit like in the example, and the negative cases, we basically, they were a bit more challenging. We had to show how we can always tweak the reductions to make sure that we can still do them, but still comply to the functional dependencies, and that we can always do that as long as the query we look at is a valid extension.
Is Q plus unit in Q?
Yes, well, up to variable
Okay.
renaming. So we also looked at general functional dependencies, where a combination of variables implies another variable, and some of these results also hold for general functional dependencies. So this was, we increased the expressivity, we added projections, we saw what happens when there are dependencies. Let's now take it a step forward and increase the expressivity a bit more. The next natural class of queries is unions of conjunctive queries. They're equivalent to positive relational algebra, they're well studied. And here we have a database that describes the conference where this work was presented. We have a table with the tutorials, which person gave which talk, and the table with the schedule, which talk was on which day. And we can ask for this conjunctive query that gives us a list of speakers per day. And now, maybe we have another table with a different type of talks. Research the talks that were accepted to the conference. And we can ask for the second conjunctive query, which asks for a list of speakers of the second type of talk per day. Now, if we only want the list of speakers per day and we don't care what kind of talk they're giving, we can ask for the union of these two conjunctive queries. That's the type of queries that we will consider now. What happens with the complexity? So we have three cases. The first case is that all of the conjunctive queries in the union are easy, and we can quite easily show that this first case is always easy. I won't spend too much time on that to talk about more interesting things. Now let's talk about the second case. So the second case is that the union contains some easy queries and some hard queries. And if you just think about the first such query that comes to your mind, just jot it down, it will probably be hard. But can this also be easy? So actually, it was claimed before that if you look only at UCQs, unions that are not redundant, and they contain a hard query, then necessarily the union is hard. And we actually managed to refute the claim and show that in the second case, even if the union is non-redundant and it contains a hard query, it can be easy. So that's the second case. And then we said, cool, we have a surprising new tractable case. We have some hard cases. Let's try to prove a dichotomy because that's what we like doing. And we said, okay, let's look at the third case and prove that it's always hard. And we tried, and our proof only worked for some of the cases. And then we realized the reason for some of the cases. So if we have no body isomorphism, I'll explain what it is later. And after we kept trying to prove lower bounds, we realized the reason we can't prove it always for the third case is because it's not true. And even in the third case, we have tractable queries. So even a union that contains only intractable conjunctive queries can be tractable as the union itself.
So Can't you have a query and its negation and always the reunion is easy? Right, so if you have a query which is hard and it's okay.
It's not all positive. It's similar symbols.
Okay. So positive.
Yes.
Thanks.
Right, what was I going to say? Oh, I wanted to say here is that I think this really shows what happened to us here really shows why it's important to try to prove lower bounds, not just from the point of view of, you know, curiosity and because it's nice to do this, because when you try to prove lower bounds, sometimes you fail. And sometimes the way you fail is you manage to prove it only for some cases, but for some other cases it doesn't work. So it really pinpoints your attention to the cases where you can find tractability. And then you know how to look there and to find algorithms for this specific cases. So let's take some more details. Here's a query from the second case, where we have a hard query and an easy query, and the reunion is easy. And this can only happen when we have what we call a body homomorphism. So the body of the second query maps of the easy query maps into the body of the hard query. So it's a mapping of the variables such that for each atom in the easy query, we have an atom of the hard query that it maps to. And intuitively, what this mapping means is that the easy query doesn't filter too much, so it can give us information about the answers to the first query. So what happens here is that Q2 computes the join of R1 and R2, which means it computes all possible values for A, B, C. And in the world of Q1, A, B, C means X, Y, Z, which is the hard part in Q1 because we have this path X, Y, Z where Y is existential. That's why it's not free convex. So we say that Q2 provides X, Y, Z to Q1. We can compute the answers to Q2, store them in this sort of relation, and then use this extra relation when we want to answer Q1. So we introduce it as an extra atom here. Again, we have an extension, and we look at the structure of this extension, and now the structure of the extension is tractable. So now we can solve the first query efficiently. So this almost gives us what we want. This tells us we can solve the second query efficiently, linear preprocessing time, constant delay. And then we can solve the first query efficiently with one linear delay step and then constant delay. So the two problems we have is that one step in the middle is linear and that we may have duplicates because the same answer can be an answer to both Q1 and Q2 and we only want to get it once. So actually we show that this is not such a big of a problem. We can handle these two things very easily. And we use what we like to call the cheater's lemma because it tells us how much we're allowed to cheat without actually cheating. And it says that if we can solve an enumeration problem where the delay is usually constant, but a constant number of times it's linear, and there are almost no duplicates, but every value we can get a constant number of time, then this is pretty much equivalent to linear preprocessing and constant delay in a sense that we can tweak this algorithm and get an algorithm with linear preprocessing, constant delay, and no duplicates.
Do you need to know the constants in advance?
Yes, you do need to know the constants in advance. So basically what you do is something like to handle duplicates, you save what you saw. If you see something you've already seen, you don't print it, which is not enough because you can see new results for a long time and then only see things you've already seen. So you also need to sort of regularize the delay. So you don't get a new answer the moment you see it, you wait a bit and then you print it and it always works. Okay, so that was the second case. Now the third case, I'll just say a few words about that. So the third case can only be easy if the queries have isomorphic bodies, meaning it's basically the same query but with different projections. Like what we see here, the projections are different. And this can happen if the two queries have different hard parts. So you can see here we have this hard part XYZ where Y is projected. But here this is not a problem because XYZ are all free. But this query has a different hard part that's not hard in the first query. So basically the two queries can help each other. And the way it works, more or less roughly, is we know we cannot find all answers to Q2 efficiently, but we can find some of them. And we show that we can find enough of them to give us all of the information we need to help Q1. So we can find some of the answers to Q2, and as a side effect within these answers to find the join of R1 and R2. Then after we do this, we use this side effect in order to compute Q1 efficiently. Once we do this, we have the join of R3 and R4, and then we can use this to compute the second query efficiently. So overall, we have 3 steps, so we can get at most 3 duplicates per answer. And again, we use the cheater's lemma, and this works.
Can it be the case that the join of R1 and R2 is much larger than the final outcome?
It can if you do it naively, but now here to compute the join of R1 and R2, we use our algorithm that does this dangling tuple removal. And this thing guarantees that the join, sorry, no, so it cannot. So it cannot, because the query is cyclic, and it can. Okay, let me restart because it was confusing. If you just look at the join of R1 and R2 out of the blue without any context, yes, it can be larger. But the way we compute this is we do it on this join tree that also contains R3 and R4. And we filter out the things that will be filtered out by R3 and R4. So I guess what I said here is a bit lying. It's finding the join of R1 and R2 restricted to R3 and R4. Good point. Good. More questions? Okay. So, so far, we discussed enumeration complexity, meaning our task was to enumerate all of the answers to the query. And now I want to say a few words about what happens when we want to do some other tasks. So I will say a few words on the types of tasks, motivate the types of tasks we want to answer, and then I'll just briefly mention what our results are like. Okay, let's recall that we have a database, we have a query, and we know that the number of answers can be very large. So our solution so far was enumeration. Let's say these fruits are the answers, right? We just print them one after the other. And the complexity measure we looked at was linear preprocessing and constant time between answers. We didn't just say we want to get all answers in time proportional to the input plus output. And so what we said is a bit more restrictive in a sense, and it makes sense when we think partial answers are useful, because then after linear time, we will already get a first answer and we'll have a constant stream of answers, and we don't need to wait for a long time until we start getting the answers. But it's not always enough to just start getting answers if you get the answers in an order that doesn't make sense and you can't reason about the other answers. Sometimes it's not enough for you. For example, here, if these are the answers and I just look at the first third of the answers, I may think that all of my answers are red fruits. It's not representative of all of the answers. So something else we could do if we want to get something that's representative of the answers is sampling. We can sample one answer, and then we can apply this repeatedly to sample many answers. But the problem here is that we may waste time producing answers several times. So what we really want is the best of both worlds, which can be seen as sampling without repetitions or as enumeration in uniformly random order. So we call this random permutation, and this is what we want to achieve. And the way we suggest to do this is to separate this task into 3 components. First of all, we count, we find the number of answers. Then, once we know the number of answers, we have a second component that generates a random permutation of the indices. So this is independent of the database. And then we have a third component that translates an index to an answer. So what is this third component? Maybe let's formalize it a bit more. We want to simulate an array that contains all of the answers. And then given an index, we return the answer in this index. And if the index is too large, we want to return out of bound. So here we don't have any constraints on the order of the order in which the answers are stored in the array. We just want to simulate this way. So if we have efficient direct access, we have the third component. And actually then we also have the first component, because if it returns out of bound when the index is too big, I can just binary search for the number of answers until I find the index where this index has an answer, the index afterwards doesn't. And the second component is something we can do using simple modification of a known algorithm. So what we really need here from the database is this direct access to answers that simulates an array that stores all the answers without actually producing the array, because as we said, the number of answers can be very large. So if we look at the three types of tasks we mentioned, direct access can be used for random permutation, and random permutation is a form of enumeration. So if we look at the Venn diagram of the queries that admit efficient algorithms for these tasks, then we have this sort of nesting. Whenever we have direct access, we also have efficient random permutation, and so on. So here in this part, when I will be talking about direct access algorithm, we will no longer have constant time per answer, but we will have usually logarithmic time, just because this is what we know how to do. We don't know how to do it with less. So this was defining what we want with random order and with direct access in order to achieve that. Let's see another type of task we want to solve.
So is it obvious how to get direct access in logarithmic time?
No, not at all. I just want to introduce the tasks, and later I'll tell you what we know about it. Okay, so the second task we want, let's say we have this input database that with information about our employees. So which employees have which roles, how much we pay a role in a specific period, and how much we pay employees according to where they live for travel expenses. And let's say I want some statistics on how much I pay an employee a month. For example, I want the median or a box plot. Or maybe I want a list of everything I ever paid an employee a month, sorted by how much I paid. But there are too many answers, so I don't want all of them in one page. I want them in pages, and I want to be able to go to any page arbitrarily. All of these things can be solved by joining the three relations, getting all of the answers, and then sorting them by how much I pay, which is in this case, the salary plus the travel cost. And then all of these problems just translate to accessing a certain index in this table. But we said that this table can be very, very large, much larger than the size of the input or the number of answers I actually want to access. So I would like to simulate this table without actually materializing all of the answers. So this is a task that's very similar to what we saw before, except now we have a specific order that we want to be able to simulate. So this is direct access with a specific order requirement. So we have these two tasks. Now let's mention a bit what we know about their complexity. So first of all, if we have no order requirements, we just want direct access. We know that if the query is not free connex, we don't even have efficient enumeration. So we definitely cannot have efficient direct access. And actually, all of these cases where we can do efficient enumeration, we can also do efficient direct access. And this means that these three classes we saw before actually collapse. So for free connex, the free connex queries are exactly the ones that admit efficient algorithms for all three tasks, and the others do not. Now, what happens if we have specific order requirements? We looked at two types of orders. We looked at lexicographic orders, where along with the query, the user specifies an order over the free variables, and we want to ask whether this specific order can be achieved. And out of the free queries, not all queries can have this order, but we identify a specific condition that's quite easy to check that tells us whether we can solve this, this order efficiently. So we have an algorithm if these conditions hold, and we have a hardness result in case they don't hold. And we also look at sum of weights orders, which is what we had in the example, where every attribute has some weights, and we want to ask, we want to sort the answers by the sum of the weights. And we found a condition where this is tractable. Unfortunately, that's a very restrictive condition where all of the free variables are in one atom, but we proved that everything else is hard with respect to these time bounds we want to achieve. Good, so that was conjunctive queries. Let's see what happens for unions of conjunctive queries. So this is just to recall what we know from enumeration. Now, what happens when we look at the more demanding task of direct access without order? Then for enumeration, the first case was always easy, and even the third case was sometimes easy. And here, even the first case is sometimes hard. So even a union that contains only tractable conjunctive queries with respect to direct access, with respect to everything, it's not necessarily tractable. And there is a very easy example actually that shows that. We have these two queries here on the slides. They're both free connects. They only have two relations, so they're definitely acyclic. They have no projections, quite simple. But if I look at their intersection, then the intersection is the cyclic query we saw before. And for the cyclic query, we know we cannot count it efficiently because that would be like counting triangles in a graph, and we assume we cannot do that. And we know that when we have efficient direct access, we can use it for counting. So if we can count, if we do have efficient direct access for the union, it means we can count the union. And since the two queries are easy, we can count the two queries, and this means we can count the intersection. So that's a contradiction. So the conclusion is that for UCQs, this thing doesn't collapse. There are queries, the example we saw before, that is tractable for enumeration, but not tractable for direct access. And we actually don't really know where the line of random permutation goes exactly in between. And something else we propose, since direct access is hard sometimes for UCQs, we propose alternatives for random permutation that do not go through direct access. Good. So to recap, we started with some introduction, understanding the basic building blocks of queries, which are joins, and the complexity we want to achieve, and why cyclicity has an important role there. We slowly increased the expressivity by introducing projections and then unions, and we saw how functional dependencies and how unions affect the complexity, and how we have more efficient cases and how we can analyze the complexity in these cases. And then we considered other tasks, enumerating with random order, direct access with or without order requirements, and so how things change for conjunctive queries and for unions of conjunctive queries. What's next? So there are some things that are quite direct next steps following the things I mentioned in this slide. First of all, and some of these things here I'm actively working on in very advanced stages. Some of these things I don't even know how to address at the moment. So first of all, we would like to achieve complete dichotomies for some of the cases I just mentioned. It can be easy, it can be hard, but we don't know exactly where the line goes. The second thing is queries with self-joins. So as I mentioned, all of the hardness results, we had some fine points at some point. All of the hardness results are only for queries where in the same conjunction, you're allowed to use the relation only once. And this is very common in database theory. A lot of the results are only for queries without self-joins. And until recently, whenever this question came up, and it came up a lot in conferences, then people would say, well, Probably we just don't have the right tools to prove that it's hard, but they're still hard if they have conjunctive pairs. And only about a year ago, we realized that it's not true, that actually self-joins can make queries easier. And now we're looking into how much, in what cases, and it gets really complicated actually. Looking at larger query classes, for example, introducing negation and seeing what happens to the complexity. So direct access, I said that direct access was hard sometimes for UCQs, for unions, because it allows counting. But the reason it allows counting is because the way I define direct access is that if the index is too large, we need to say out of bound. What if we just say that if the index is too large, we're allowed to return whatever we want? And we can no longer prove that it's hard. Does it all of a sudden become easy? I don't know, I doubt it, but maybe. Enumeration lower bounds. So the type of lower bounds we saw were only, we cannot find the first answer in linear time, or we cannot find all answers efficiently. But we don't really have tools that tell us we can find some of them, but not with this specific delay, not with this order between the answers, even though you can find all of them. So these are tools that we are currently lacking, and will be very interesting to see if we can find something along these lines to help us. I focused on the very, very tractable cases, linear preprocessing and constant delay. But what happens, we know sometimes it cannot be achieved. So what happens when it cannot be achieved? How much time do I need? This is a very interesting question. Also, space consumption, we only talked about time. We know that to achieve this, sometimes we had to store all of the answers we've seen, which takes a lot of space. We know that sometimes we can avoid it, but we don't know exactly when. So that's interesting. And also applicability in practice. Some of the things I mentioned here were implemented. We had some very preliminary experiments that look good, but how good they are, can they really be competitive? This is something we should look into. And maybe I'll briefly mention some additional work that's not exactly within this line, so I didn't talk about it a lot in this talk, but I also worked on finding 3D compositions, which can be used as query plans for the hard cases. So if the query is not naturally acyclic, we can make it acyclic during preprocessing using 3D compositions. And finding a good 3D composition is a hard problem that we worked on. And also I did some work on what happens when you have some uncertainty and probability within your databases. So if your database has some noise and you want to repair it, you want to eliminate the bad tuples you have inside, how can you do that? And how can you model and represent cases where tuples are true with a certain probability? What happens in this case? Okay, thank you.
Questions? So, Nofar, have you looked at what happened with bag semantics? If you don't do duplicate elimination?
We don't remove duplicates. I didn't really look at it. I can imagine that it will sort of be easier for the specific problems we talk about, because then all of the projections don't make a lot of difference. And then it boils down to cyclic or not cyclic. But I didn't really look into that too much.
You mentioned functional dependency, which are properties of the actual databases, but other than that, all the harness or the algorithm work for based on the queries only. So are there additional properties of, are you considering additional properties of the actual databases that could make the queries harder or easier?
That's a good point, because that's another future direction that I didn't mention. So there are a lot of other kinds of dependencies that are common in schemas of databases, and they could also affect the dependency, and we didn't really look into them yet. But it is interesting to look into them.
And also maybe sometimes not just dependencies, right? Like
Yeah.
in probabilistic databases where you look at a particular combination of query and database to lead to particular shape of the provenance or something like that.
Yeah,
maybe if you have like a bound on the number of occurrences of each, I don't know, value in a column or.
Yeah,
all
so
kinds of-
I didn't mention it, but I mean, there is some generalization of functional dependencies where it's not just that one attribute has one value, but one attribute has at most a constant number of values, and then our results also hold for that. So then if you know that every value appears at most a constant number of times, even regardless of an attribute, that will also go inside that. We would be covered by that.
Like ordinality constant.
Yes.
Yeah. Any questions? So let's go speaker again.
עד שנגמרו הדאטאבייס ואז שנגמרו הדאטאבייס.
לא, זה ליניאר מספרי. לא, זה נשאר ליניאר מספרי.